So what is HPAT? High Performance Analytics Toolkit, HPAT, is a compiler-based framework for big data analytics and machine learning, and it turns out some similar domains. And I'm going to discuss what similar domains would work. So the goal is to provide efficient, large-scale analytics without sacrificing productivity. So we want to have, this works, we want to have array-style programming as well as high performance. And the way we do it is by building this on top of parallel accelerator, using domain-specific compiler heuristics for parallelization, and using efficient high-performance computing stack like MPI. So we will bridge the enormous productivity performance gap. And I'm going to discuss all of these in separate sections, what they mean. So let's look at a very simple data science application. Just simple Julia code. Let's say these points and responses are some small data, small metrics of features. And I'm going to run some logistic regression algorithm. Gradient descent, simple math formula written in vector style code here. Easy to read, similar to the math formula. The domain scientists in whatever domain, they can understand it easily. I'll let you look at it for a second. Just matrix and vector operations here. And W is the model we are training. So what about large data? What if it would take forever? I have terabytes of data. It doesn't fit in my memory, and it would take forever. I need parallelism. Essentially, I need a cluster instead of a single machine or cloud. How would we do this? There are multiple approaches. You can go what I call the gold standard way, write MPI C++, the same way scientists at national laboratories write code, nuclear simulations on large-scale supercomputers, DOE labs. You could use MPI in Julia. You could use things like Spark, which are essentially libraries. I'm going to describe them a little bit. Or you could use HPAT, which is sort of a smart compiler. So the first approach, MPI C++, uses, if you are not familiar, message passing interface, passing messages across machines, right? It's going to give you the best performance. Hands down, people on supercomputers use this. But you need to understand parallelism. You need to understand MPI. You need to do parallel I/O somehow. By parallel I/O, I mean loading some files, some data efficiently on multiple nodes, which is not exactly easy. And of course, C++ crap. It's tedious, error-prone, has nothing to do with the math formula. The code, I don't want you to read it, but it's just a small portion of it, C++ code. And it's not readable. I couldn't even fit it in a single slide. The other way is using MPI.jl. Essentially, do message passing across machines explicitly. So some sort of MPI.jl code. It's less effort than C++, obviously. It's in Julia. But you need to still understand parallelism and MPI. And you need to do parallel I/O. I still don't know how to do that in Julia. I think there is enough support yet. And you need high-performance Julia. With basic Julia compiler without parallel accelerator or HPAT, you might end up rewriting your code in some sequential for loops instead of matrix vector operations. And also, there are some infrastructure challenges of deploying Julia on large-scale machines. They might not have full Linux, not enough support for LLVM. LLVM might not vectorize properly, so on and so forth. What about these new frameworks? Spark, super famous. So they provide some map-reduce library. Essentially, you divide your computation map and reduce sort of functions. The map function calculates this gradient, the same math formula. The reduce function says just add them up. You tell the library, this is my map function, this is my reduce function. And this library has some sort of master executor model and orchestrates the parallelism on the machines automatically as best as it could, and as it can. So it's easier than MPI C++, obviously. And these libraries come with a huge package of things, a lot of features. If you are doing streaming, they have some support, limited but still, and so on. So but still, you have some development effort. More importantly, these things are very slow. It turns out that these days, a lot of people, a lot of scientific computing, more serious people, not even trying it anymore because they use Python MPI or hopefully soon Julia MPI. So these things are 100 times slower than MPI C++ easily. I have some crazy cases, but there are the kind of corner cases more than this. So you have the overhead of host language, these NumPy operations or whatever array operations, whatever language you are using. You lose locality across operations. The library can't see what's inside the operations to optimize them across multiple operations. And these libraries have a lot of overheads. They have to schedule all of the work across different machines. So our approach is HPAT. What if we could convert that Julia code to MPI C++ or something equivalent to it, hopefully just Julia at some point, automatically? 3 decades of computer science research shows that parallelizing compilers, a compiler that would take any program and parallelize it, they just don't exist. It's not practical to do that. But in this case, we can do something. A few observations. Array code is already implicitly parallel. When you say this vector plus that vector, it means it's parallel. You don't specify any order. And also, parallelism is very simple for data analytics and similar domains. You have some sort of map-reduce pattern, data parallel pattern underneath the computation, whatever it is, even though you're not writing map-reduce code. That's why these libraries have been successful, like Spark, because they provide map-reduce, which is natural for these domains. And you have one-dimensional decomposition, meaning that you just divide the data in one dimension instead of other things. For instance, if you are solving PDE on 3D domain, it's better to divide in 3 dimensions. So in this case, one-dimensional decomposition is enough. And the communication is very simple. It's R-reduce. You come up with your model on every node and just add it up, somehow reduce it, and then broadcast to every node in each iteration. The communication pattern is very simple. So we are saying for this case, we can parallelize this code automatically without any change, almost no change. So assuming that this is your matrix and the features are across columns, each column is a sample, and these are the labels, a vector, and this is the model you are training. After 1D decomposition, this compiler should come up with this. Divide this matrix in this dimension across the columns, across the samples, divide these labels or responses the same way, and replicate this W and do all the communication and parallelization necessary in the rest of the code. So this is what HPAT does. So look, going back to our code, the same formula, we have to do just a few things to get it running on a large-scale system with HPAT. Just this annotation at ACC HPAT, at ACC comes from compiler tools package, which is used by Parallel Accelerator 2. We also need to get the data from somewhere. So we sort of made up some syntax. I'm still not sure if this is the best, but it's been working so far, for specifying the data. So you say data source of type matrix flow 64. It's HDF5 format, famous storage. This variable in HDF5, and this is the name of the file. This is the only change compared to the previous code. In the previous code, the data could come from anywhere. It could be just argument to the function. But here, you have to specify the data. And then you just launch Julia with MPI run, the same as, or whatever your cluster or cloud infrastructure provides. So you just launch it, in this case, on 64 nodes. And for this example, I'm going to show you it's going to give you 95 times speed up over Spark. So it's huge. What comes out of HPAT essentially is some MPI C++ code that does a lot of things automatically. The initialization and partitioning, initialization of MPI and everything, partitioning of the data, every node knows where to start, where to finish, allocations, dividing the allocations across nodes, and then parallel I/O calls, sometimes these are like 200 lines, but HPAT can generate with the basic information. Then computation in a fused way, maximum locality. Every data that comes is consumed for all the operations. And then communication, a lot of the cases are reduce or sometimes broadcast and other things. So bare metal MPI C++ code with near zero overheads. Nothing, there is no runtime doing random things in the middle, nothing else. How much time do I have? Okay. So how should we use HPAT? The dependencies are parallel accelerator, parallel HDF5 library. Remember, if you are installing it at Ubuntu, it's different than normal HDF5. You have to say parallel sudo apt get parallel HDF5 when you're setting up your system. And you need MPI, which is easy to install. Just annotate the functions with this @acc annotation. But the computation has to be implicitly parallel. You just need to use matrix vector operations and comprehensions, essentially things that parallel accelerator understands underneath, because parallel accelerator is giving a parallel representation to HPAT to work with. And there shouldn't be any bad for loops. I call loops that could be written by matrix vector operations bad. Like iteration loop of a solver is naturally sequential. You have to use a for loop. But loop for something that's parallel is bad in this context. Because, as I said, decades of computer science research shows that you can't analyze every loop and come up with parallelism. So you have to use column major matrices, as good Julia programmers will all do. And this is what the compiler assumes. And sort of all of the program should be inside HPAT. You can't really say this part inside HPAT, some part I don't want to use HPAT because it has to know everything to parallelize everything. You don't have a shared memory to just read something out of another operation. And I/O should be done with this data source syntax. And HPAT, as I said, does everything else for you. What are the limitations? Making a compiler robust is very difficult. So this is in research prototype stage. So the compiler analysis might have limitations. It needs very good coding style. But there is a fallback. If HPAT couldn't understand some code, you can kind of write explicit map reduce and par4 code yourself. So there is a fallback if it failed. The other limitation is that right now is that only map reduced kind of parallelism works. Anything that could be data parallel. For instance, if you are doing PDEs, a lot of the time it's better if it's multidimensional parallelism, not one-dimensional parallelism. Unfortunately, we don't have sparse matrices yet, something on the to-do list, but hopefully we will get it working soon. Right now, we are mostly working with HDF5 format for files, but we are thinking about adding other formats to like netcdf or tiledb or other things. We have some support for text files, but it's buggy. Using text file has a lot of downsides anyway, so not using it is best. So what is the secret sauce? How does this work? The secret sauce is this array distribution inference algorithm. In the beginning, so we want to partition these matrices, these arrays this way, and we want to replicate this guy, my model guy, this way, and make everything working, communication, and so on. At first, in this algorithm, we assume all arrays are partitioned, starting from that. Then we run some iterative algorithm until it converges. In each step, it can assign some other arrays as sequential too. So it walks the AST in each iteration and runs some rules depending on what it sees. For instance, a very simple one, if you have some assignment, left-hand side and right-hand side, both of them should be either sequential or partitioned. That's very simple. But sometimes these rules can get more complex. For instance, if you have matrix multiply, there is some gem called gem operation in the AST. Some rule says that when you do this operation, labels times points, for instance, because we know that the columns of matrices are features of samples, we can know that the output is the model in this case, or something sequential. So we assign this W guy to be sequential, these guys parallel, and also we need some reduction to accumulate the result of this multiplication to this model. And we know some other calls, some other operations that we support, a lot of rules. If something is not known, something random in the AST, then it gives up. It assumes everything is sequential in that, which is not a bad thing. You can have some things to compute some constants that could be sequential, not much computation there. But this can be bad if there is something that HPAT should know about. So the compiler has a pipeline like this. At first, you have this Julia source code. It goes through some macro paths to desugar whatever is there, like data sources. Then Julia compiles, get this AST out with code typed standard way. Then go through some domain paths, which prepares the AST for parallel accelerator. Parallel accelerator has this domain IR and parallel IR passes, which essentially extract parallelism from the code and do some optimizations. Then distributed paths distributes the code across machines, partitioning arrays, and so on, generating communication. Then the CGen module of parallel accelerator, we extended with some other C code generation routines, generates C code, MPI C code. Then your MPI C++ compiler compiles the source. This is how it works. And actually, that function becomes a shared library that Julia calls to, if you are using it inside Julia, or you could use it standalone. So these pipeline passes, as I said, this macro path just desugars some extensions like data source that might not be valid Julia code, similar to other macros. And we had a lot of examples here. This domain path generates some things in the AST, for instance, for these data sources, allocations, variables, function calls that parallel accelerator can understand and optimize. Then this distributed path, as I said, partitioning of arrays, dividing allocations, using some distributed memory libraries you might have. I have some example later, and so on. Backend code generation, just generating C code. Looking at the results, so we benchmarked this on some local servers, as well as this supercomputer, Cori supercomputer at Lawrence Berkeley National Laboratory in California. So these blue lines are Spark, red lines are HPAT. We have speed ups from 23 times on up to this 1600 crazy speed up. The first benchmark is 1D sum. A huge vector, just sum it up. Load it and sum it up. Very simple. The second one is the same, except that it filters the vector to some only values greater than some constant like 10. The third one, this is Monte Carlo Pi example, which is widely used, even though it doesn't tell you anything. But I just wanted to mention that it's so much faster because that Spark library doesn't know what's going on in the whole program, creates a huge array of random numbers and computations, then does the reduction. But in HPAT, HPAT can get rid of that huge array. So it's doing the computation in memory versus doing it in registers. Huge difference. And also there are some library overheads on top of it in Spark too. This is a corner case. I don't think it happens for a lot of useful cases, but good to look at it, some insights. Logistic regression is exactly the codes I showed you, no change. K-means is interesting because it's written mostly in comprehension syntax. In Julia, you can look at the package repository. The code is very short, a few lines. In Spark, it's using key value stores and some weird abstractions that I don't know how they came up with that code. It's very difficult to write that code. The speed up is only 23 times because HPAT needs to do some compiler transformations that it cannot do right now. So the code that HPAT is generating is not optimal right now. So the speed up has to be way more than that. Something else on the to-do list. Looking at scaling, going from 64 nodes of this Cori supercomputer to 256 nodes with the same data set size. I think it's 400 gigabytes or something. I don't remember the exact data sets. I think 2 billion samples. The gap even widens on this 256 nodes. HPAT takes only 4 seconds, Spark takes 600 and something seconds. So what about machine learning libraries? A lot of the times, people just want to load data and run some machine learning library. In Spark, you guys are probably familiar with MLlib, very famous, right? So we have to do the same thing here. Looking at this function here, there are essentially 2 lines of code, this data source, and we want to load this data source and just run k-means. Very simple. HPAT uses Intel DAL. DAL stands for Data Analytics Acceleration Library. To do the actual k-means, the interface to this library, which uses MPI, has some MPI interface, is very complex. You have to set a lot of things up to use this library. But HPAT can generate all of this code. Since it has the data source in it, it has all the information to generate this code. So this 2-line will become a few hundred lines of crazy C++ code, but it will give you great performance and actually better numerical results than MLlib. I wanted to talk a little bit about building a compiler in Julia, the experience we have had with Parallel Accelerator and HPAT. I think Julia is a very good language for building compilers. And we just need to clean a few things up to make that happen. The good thing about Julia in general is that it has built-in type inference. Similar systems, let's say MATLAB, Python, they just give you a parser. They don't do anything else for you. Here, you have a very good macro system. Then you have the same parser. Then you can do type inference optimizations by the Julia compiler, get the AST out, do whatever you want with it. So we can build a lot of advanced tools in Julia. And I think the community is on the right direction. I saw a lot of good tools with macros and things like that. But the downside of building a compiler in Julia is that we don't have a detailed AST definition or API that Stefan talked about this morning. When we get it, building these tools is going to be so much easier. Right now, we don't know what the AST contains. There is no contract between Julia compiler and tools. We can expect, you can get surprised easily. It can inline something. It can generate any code out of the user code. The other issue we have right now is that the first time you use a package, it tries to load and compile it, right? We saw in demos yesterday, especially that people were starting something, talking, then getting back to it so that the package is loaded. Here, these two packages are so big that it takes a long time. On a fairly high-end workstation, it takes like 35 seconds for me. So I'm just walking around the hallways until this happens, trying not to waste too much time. And it's mostly because I ran vtune. It's because there is type inference every time these packages are used. So you use HPAT for the first time in Julia. It does type inference on parallel accelerator, HPAT, compiler tools. But we don't need all that to happen. And I think static compilation is on the right track for Julia 1.0. I wish we had some tool to tell us, hey, do something with this piece of code, this function. It takes a long time to compile it and infer types for it. This would help us significantly in this project. So what are we working on next? Something that I'm really excited about is doing structured data processing. Essentially, we had a lot of talks about type tables, data frames, things like that. So we need structured data processing for analytics, but we don't want to use SQL. Right now, there are systems, if you guys have heard of them, Impala, Hive, Spark. You have to write some SQL code, then get the data out, then stick it into something else, do machine learning, array computation, whatever. They are very difficult to use. So we want to do complex analytics all in array syntax, all in Julia, no SQL. And this is inspired by some benchmarks that I looked at a while ago and discussed with my colleagues. This is called Big Bench, essentially simple analytics tasks. Assume you have a lot of users, you want to see how many items they bought and build some machine learning model for them. Very simple tasks, but the code is very complex because you need to do advanced SQL to set up the matrices for your analytics. So we want to have array syntax for this table operation like join, filter, aggregate, similar to dataframes.jl, but richer, with more features. So one example is here. If I want to aggregate and sort of count the number of items a user bought in different categories, I can just have this syntax and say, create this column for me with aggregation on my users and say class 1, class 2, class 3. So essentially, it will becomes a matrix ready for machine learning. And there are some other use cases. For instance, 2D decomposition, we have some collaborators who want to do matrix multiplication of 2 4-terabyte matrices plus some array computation. How do we do that? Just some basic 2D decomposition can help here. So in summary, High Performance Analytics Toolkit provides scripting abstractions for data analytics and similar domains, but provides bare metal performance as well. Matrix vector operations, extensions for parallel I/O, domain-specific compiler techniques let us generate efficient C++ code and use existing libraries. And it's so much easier and faster than alternatives, as I mentioned. I encourage everyone to get involved, any sort of contributions if you are a CS student. And we need a lot of use cases to make sure it's on the right track. We have a huge to-do list. We don't know which items are actually useful in real applications. So if you guys can try it out and give some feedback, that would be very useful. Thank you.